All right, let's talk about, okay, so I don't have the chat open, so if you want to ask a question, just unmute yourself and add it. Okay, so this is an introduction to IP-based networks. There is a lot of definitions, and there's this theoretical open source interconnect layered model. No actual network uses it directly, but all the networks sort of make a translation between what they do in layers down to this OSI framework. There's a picture of the Lab 3 choice. There's only actually one Lab 3 choice other than open-ended, and that uses a robot together with a CC3100 to connect the robot up to the internet. I'm not going to get to the CC3100 today, but I'll get there eventually. I got a pretty picture that shows Metcalf's law, so I'm going to show that to you again. And then basically we're going to do an introduction to the internet. Any questions about stuff before I get going? All right. Yeah, this was a slide from McDermott, by the way, who teaches 445L. And when he gave me the slide, all he did was this. And I go, okay, what is TLA? I had to look it up. I didn't know what TLA was. It obviously stands for three-letter acronym. Not all of them are three-letter acronyms, but there's a lot of acronyms. We're going to see the Internet Protocol. We're going to see the domain name system service. I think that's actually a typo. I think it's called service. But that may be one of those things that people, you know what other people call DNS?
Pretty sure it's domain name system.
You think it's system? Okay, fine.
Yeah, according to Wikipedia.
Okay, fine. We'll let McDermott win that battle. Okay. Transmission control protocol, user datagram protocol. We will see the transport layer, and we'll see the network address translation. But there's a lot of acronyms. Okay, so this is there's two pictures that are essentially the same. This is a picture that actually Yarabali made for me when we did the MOOC, the edX massive open line class. We added a Wi-Fi internet lab to the internet. I mean, to the massive open line. And so this was the mapping that Yarabali gave to me when we did that. So on the left are the open source interconnect layers, and on the right is the internet protocol. And the colors represent the mapping. Okay, so the second lecture in this chapter is Ethernet, and then I don't know, third or fourth or somewhere we'll do Wi-Fi. Okay, so and we talked about the advantage of layering before, as you can. This is an abstraction process where you can build and use and translate and replace. Okay, and so the MAC layer, the physical layer, typically exists a lot in firmware, some software, but all the other layers are pretty much software. And this is another name for this is a stack. This is called the stack, the internet stack, the IP stack. These are the IP stacks, the layers. Okay. And from the previous slide, we can see the Internet Control Message Protocol, Internet Group Message Control. That happens in here. Okay, so that's and then this is pretty much the same picture, and the groupings aren't quite the same, except obviously this part's the same because that is the OSI layer, and then over here is the IP mapping of, and he's got some more things in there that so if you look at FTP exists in this in STM that existed in the same two layers over here, and the TCP occurred here, the IP oops yeah down here. So there's not a lot of disagreement in how this thing overlaps, except most internet stacks don't have 7 layers, I guess is the point of this. And again, so this is a picture from the book. And so obviously as you go down, it gets more physical, and as you go up, it gets more abstract. Okay. So things like FTP servers where you're sending files and doing remote access, that's one of the highest level. And what we're going to do in the second slides for today is very physical, has cables and voltages and stuff. This is a picture. Did I show this one to you before?
No.
Okay, so this is the animated GIF that I made. When I made it, I was sort of motivating the need for a network. Okay, and the picture was supposed to represent as you increase the number of nodes, if you had a physical connection between all your nodes. In other words, if you had 13 nodes and you wanted a physical connection between each of the 13 and the other 12, it would take 78 cables. Okay, but it's also the proof, I think, of Metcalf's law, and that is if you assign the value of the network as the number of links, the number of possible interconnections, and then it grows n squared. It's just an obvious. That was the answer to this was the proof of what I wanted from the exam, is you make the assignment that the value of the network is defined to be obviously it has a lot of flaws in terms of connecting two device. Anytime you connect two devices together, there's a value that's a constant. And as the number of nodes increases, the number of possible interconnects grows n squared. This is a cartoon of the internet. And so, what is an internet? It's a way to connect things together. And there's a couple of terms in here that we'll see. We're going to see the router in the next slide. The router connects a local area network to the internet. You see, the router typically has on one side of it a link into the internet, into the green things, however you pay for that. And then on the other side are local nodes that are physically close to the router. Okay, we have the bridges, right? Either the cable or the DSL or the backbone connection, or fiber optics, or Google Fiber, or AT&T Fiber, are connections. Those are the blue ones connecting into the internet. We obviously, given the nature of this class, we're going to talk about the pink things and not the green things, given the focus of this class. And then within the local devices, We'll have an access point that'll be necessary for Wi-Fi. This will be a Wi-Fi thing. Come on, get in closer and draw prettier, John. Wi-Fi here, the access point, which can be your phone or your local or your wireless internet in your house or your car, everywhere. And basically, we're going to be able to send information from one node to another node. Okay, that's the idea here, is these nodes, these yellow nodes represent possible connection spots that we can interact with. And they're drawn in different shapes and sizes because they're the circles are wireless nodes, and the rectangles here are physical wired nodes. Okay, that's obviously we've been doing this all semester. Yeah, this is consistent with the textbook definition, and that is a smart object is another name for a thing on the Internet of Things, and it has a computer in it. It has a microcontroller in it, not a general purpose computer. And as you know, as we've noticed all along, to create these objects, we're either going to record information from a sensor or a suite of sensors, or we're going to affect the world with actuators like servos and motors and solenoids and that kind of thing. But the smart object will then participate in the Internet of Things. This is very similar to the picture, to the definitions we created in the first couple of slides. This is a combination of challenges both for IoT and the internet. Some of them are from the book, and some of them are from Yarabali, and some of them are from McDermott, which makes this a very powerful field to work in. Oh yeah, speaking of Will, can I stop for a second? This reminds me. No, discard. Okay. I got an email this last week. Where did I put it? I put it in down. Yeah. I don't know if anybody's looking for money, looking for work, but where's her name? Nanshu Liu is a professor. I think she's actually in aerospace, of all places. I don't know why, but she is obviously. This is a she's looking for grad students. She just got a big grant. She does some really cool stuff. This is a printed circuit board tattoo, and basically there's a couple of chips on there. Okay, a couple of discrete, physical components soldered onto this this tattoo, which is basically a sticker, and all sorts of different technologies to make that happen. But she's looking for somebody with IoT and embedded embedded. Yeah, you can see. Yeah, and she does. I've sat on a bunch of her. I've sat on a bunch of her PhD committees. Yeah, she's pretty nice. She's pretty nice to her students, although, as you can tell from the pictures, this is not a theoretical research group. This is a very practical research group. But I will post this up on. I'll post this flyer up on Canvas. Anyway, just want to remind myself to remind you. Okay. So if you know of anybody looking for a job with skills that are, these kinds of skills, Ubiquity means obviously it's everywhere. Longevity means some of these things last a long time. The whole field exists because of the standardization. Okay, so now we are going away from the personal area network where you basically had control over both sides and you owned both nodes and you could, you could make it as funny looking as you wanted, to a situation where you have no idea who you're talking to. And so in order to talk, it has to be standardized. The example at the end of the next lecture is a lightweight stack, which is not all of the internet. So this is a this is a common approach to IoT in the internet protocol field, and that is don't implement it all, just implement some of it. And so they have there's a bunch of embodiments like this that allow you to get stuff done without requiring your IoT device to be full featured. Okay. Like it's the same thing with standardization is you've got all sorts of technologies that you want to deal with, different companies, different vendors. This like most fully developed engineering disciplines is evolutionary. In other words, it changes always. It's continuously changing. From a educational standpoint, it's both a blessing and a curse, and that is by the time you figure something out, it is obsolete. If you understand it, it's probably obsolete. And so it's kind of exciting to be in a world where you have to constantly learn. And so from a career standpoint, this is not the kind of thing where you do the same thing over and over again. You do the same sort of things, but everything changes. And it changes a lot. Okay. Obviously, some of these things are remote. Okay, and they're inside your car, they're inside your home, they're inside your your watch, and so they're basically unmonitored, unmanaged, and so they have to be stable. In order to deal with complexity, we need the abstraction. Live, said this before, lives are at stake. And so it must be reliable. This is something where the business people love to get their hands in because supply chain and IT, the information technology departments, because of the size of these fields, they have to be managed, or they should be managed. And so there's a whole business side of this thing, that just how do you manage these devices? So if you're working for a company with 2,000 trucks, all with IoT devices in it, you're going to have to manage. We've already done the billions, okay, but obviously when we did labs one and two, we were talking about 2 elements in our network. The ZigBee might have been 20, but now we're in the millions. Okay. And as the system gets more remote and more unsecure, securing the data will be a yeah. Here's an interesting thought. I mean, have you thought about what voting is going to be like 50 years from now? Yeah. How do you deal with I've seen how the medical field in terms of data security has changed, right? It used to be a piece of paper and handwritten scribbled information, and now it's all cloud-based and whatever. So anyway, this is a slide we've actually seen before, but to remind you that it's really pretty exciting field to be in. All right, so here's our layers. These are IP. Again, IP is the internet datagram, and on top of the okay. In the next slide, we're going to do Ethernet. Yeah, we've already done 15.4, but in the couple of slide decks, couple of days, we'll do Wi-Fi here. But on top of the physical layer is the IP, and you sort of get the idea that the way these layers work is every time it goes through a layer, it slaps on another header. And we'll see what's in the Ethernet header in the next the actual let's see what I'm going to do. The actual lab 3, you deal with it at this layer. Okay, so when you fetch information from the weather, when you fetch information from the get weather, you slap on the get weather application header and the application data. When we do the ITFF, you know, we do the if this then that, yeah, ITTF, if this then that, okay, IT whatever, IFTT, I guess is probably what that's called. Yeah, we'll also have a application header followed by user data. Okay, and then once we make a TCP request to the IPs to the stack, it'll add this to it, and then once it hits the internet, it'll add that to it, and then once it hits the physical layer, it'll add even more. Okay, so from a lab standpoint, we're going to see this. This is the part we're going to see, and the other stuff we're going to buy. But nevertheless, it is layered. Yeah, service. You call this a system? Yeah, I don't care what you call it. It's just, yeah, we're just. Okay, so we'll see that there are two types of IP addresses. Well, there's two formats, but there's the private address and the public address. And the basic, if you remember, the model of the internet is essentially two networks with a bridge, right? So if you go back to this slide here, there are two networks with a bridge, and now we're focusing in on this here, okay? And so inside the local network, the intranet, is something that will do an address translation. So the devices, the physical devices inside of this protected world will have these addresses which are not publicly accessible, okay? But when a packet comes in, okay, this network address translator will, if allowed, if the port is open and the security is right, will allow that packet to be routed to one of these local networks. So if you open up your, you know, your router in your home and look at the devices that are connected to your router, there'll be addresses like this. Okay, these will be the local addresses, and so that network address translation is the thing which gives that translation. Now, the domain name system is the thing that converts the name, like, you know, www.google.com, converts the name to an IP address. Okay, and again, you'll see that when you do the lab, is that you will send in a string. You know, you'll send in a string like this, and you'll get back an IP address. Then you're going to use that IP address to send a TCP packet or whatever it is you're doing. And that's the domain name system, apparently. What's next? Okay, so yeah, so that's okay. So next one I want to do is I'm going to do the Ethernet. Okay, okay, so thing. Yeah, so what did we just do? We basically did a high level topology or layered approach to the internet. Okay, all right, let's get physical. Discard times 10. Okay. Most of this came out of the 445M book, a little bit out of the 445L book. This is my demo. I got to go into the office and get it. Okay, not going to talk. That's not what we're doing here. That's not, let's get to, okay. So here's Bill Bard's definition of a network, and I gave this to you before, just to remind you that a network is two things: interfaces, and which include a physical media and a data protocol. Okay, so it's both a way to communicate and which is the physical media and the format of the data. Those two things combine to create a network. We didn't do ZigBee yet, but this is actually the same picture for the IEEE 15.4. Again, this is an example of a physical media, which is 2.4 gigahertz with the appropriate encoding, the modulation, demodulation, together with the packet structure. Okay, so a way to communicate, and the personal area network coordinator was the thing that could connect things together, and depending upon the architecture of the network, we either had a full function or reduced function device, and that was the same. This was the same protocol. So here's an example of a network. Again, a physical media that allows communication and a data protocol. All right, let's talk about Ethernet. And the way to think of the layers is you go from abstraction to abstraction, right? So you go from a high level to a high level, but that's not how it actually works, right? It has to go down the protocol stack into something physical, and then we need a physical connection, okay? So we're going to start with Ethernet, which is a way to connect to the internet. So, okay, so you have a IoT device or a regular computer with an Ethernet port on it, and you hook it up to a router, okay? And that allows your TCP, the router, you remember, is the connection to the internet, and it allows your packets to go in and out of the internet, okay? And so as the packets go across the internet, it obviously comes back in that direction, okay? So then we have a packet hopping down the layers across the physical layers. Okay, so that's actually just the same picture we just did. But we're going to talk about this layer here, okay? Which is, we're going to talk about the Ethernet layer with the media access control layer. All right. I mentioned the private IP addresses, and there are 65,000 of them that begin. These are 32-bit IP addresses and not 128-bit ones. But these are 32-bit IP addresses. And for this particular set of IP addresses from 00 to 255, it's one of the more common local IP addresses. Now, the syntax here, obviously, this is just a 32-bit number given in byte form, right? 1, 2, 3, 4 bytes. So each of the dots separates an 8-bit byte, which is concatenated together, unfortunately, in big Endian form. I gave that on a 445L exam once, and that is, I gave them it's one of those deals where I gave them a software that basically converted big Endian to little Endian and asked them what it did. But anyway, nevertheless, it's these are the local addresses, and again, the network address translator in your internet will convert the packets coming into your network and packets going out too, because it's got to have an outward facing IP address as well. Okay, so there's our Ethernet packet. We're going to see it a couple of times. That there approximately either a small amount of bytes. So if you have 6 bytes of application data here, then you have 46 bytes of IP gram datagram, together with 22 bytes in the front and 4 bytes at the end for error checking. Okay. And embedded in these bytes are obviously the IP address and the various informations that that will help it route. Again, so there's the layered thing. Here's some definitions you probably already know. I don't know if you're old enough to have hubs. Anybody ever used a hub? You may not ever have used a hub.
Just on my car.
No, yeah, Mike. Yeah, hubcaps. Yeah, hub was one of the first things they came out for home networks, and basically it was no more than a connector. Okay, a hub basically was a fancy socket, a fancy mechanical connection between all of the pin 1s and all the pin 2s. So on a hub, when a packet comes in, it goes to all the nodes, and the nodes had to filter out. But it was fairly simple and obviously very inexpensive because there wasn't a lot of silicon in there. It was fairly reliable because there wasn't any silicon in there. It was basically unpowered, and it was basically, like I said, a connection, outgo equals income, but switch is the more common way to do it now, and that is, you have a room with 6 devices in it. You have a switch, and you connect the incoming internet to this. That's just an incoming. This is not a router. A router is the thing that goes to the internet. But a switch basically is a smart device, and so when it sees an incoming packet, it knows which of the devices that packet is meant for, and will route it. It will send it. Sorry, route. I don't want to use the word route. Send it to the appropriate device. So if you have a lot of nodes, or if you have a lot of traffic, there's no extra stuff. There's no extra filtering that has to occur with a switch, because again, it needs. These are all the local IP addresses, and so the packets with the local IP addresses are sent to the appropriate device. And then, as we mentioned before, a router will connect 2 networks together, and then typically a router connects your internal home network, whatever, to the internet. Okay, it's a router. Yeah, it's built some cables. It's one of those things. When you're a 319K TA, you know, sort of a, you know, sort of, or a 302 TA, same thing. When you get your hands on a brand new freshman, you'll go, well, you got to learn how to solder. Okay. And the kids hate it, right? Because it's all a mess and whatever. But boy, if we were not in a pandemic, I would make you go to lab and build Ethernet cables. Okay. Again, it's one of those, you know, rite of passage things that, yeah, if you're gonna be a network person, you ought to make Ethernet cables. And this is the standard connection between the, I don't know if you ever ripped the Ethernet cable apart, but it's got 8 wires in it, and they're colored white, orange, orange, white, green, blue, white, blue, green, whatever, white, brown, and brown. And they're twisted pair. And so it's differential voltage. We'll see this, we'll see what the voltages look like in a minute, but it's differential voltage. Yeah. Is this full duplex or half duplex? Can packets go in both directions at the same time or only one direction?
Both direction, right? Send,
Yeah,
transmit and receive.
Yeah, you got to transmit, you know, left to right pair and a right to left pair. Okay, so you can just full duplex.
What are the unused for?
Oh, for extra stuff. Yeah. Yeah, sure. Future expansion. Yeah. I mean, you're going to build a cable, you might as well put stuff in there that might. Okay, somebody chatted something. I don't have the chat open. Power. Okay, fine. Power. Thank you, Austin. Austin says that you can use them for power. All right, so is this the next one? Hope I did. Did I do this right? Okay, now here we go. More stuff. This is the typical Ethernet wiring diagram when you connect up a embedded device, an IoT device. As I showed you in the previous picture, when I get into the office and get my demo and bring it to you and show it to you, it's going to use a TM4C, which is an Ethernet ready microcontroller, and plug the cable in. And so the switch or the router has pin 1 and 2 as the receive data, and the physical device has pins 1 and 2 as the transmit data. So a straight through cable, works for a device. If you wanted to connect 2 physical devices together, 2 devices, right? Then you could cross the transmits to the receives and the receives to the transmits. And the first time I taught a lab, I made which was the lab assignment was to connect 2 microcontrollers with an Ethernet. And I made all the students, this was 445M before it became an operating system class, made all the students build this cable, right, to a little wire chunker, the crimpers to make this cable. And then the cables got all jumbled up in a pile, and there was, great concern that all these cables were unmarked. And so we had a big pile of cables. So we thought I'd test them all. And every single cable worked, even this one, even if you tied pin 1 to pin 1, rather than pin 1 to pin 3, it still worked because the machine was so smart that if you connect 2 devices together and tie the 2 outputs together, it goes, oh, okay, I can deal with this. And it had a automatic pin swapper at the physical layer that swapped the pins, so it still worked. And so, yeah, I was all sure nothing would have worked, but Yeah, that was a learning experience for me to mess up. But technically, if you're going to connect to identical devices, it's typically a good idea to connect the transmitter to the receiver. But this particular device would swap the 2 pins if you needed it. Obviously, the physical layer is the media access control layer. And so this, like in the TI world of things, is actually a lot of silicon and a lot of digital signal processing and a lot of low-level devices. And now RJ45 is the connector type. All right, so here's the fun. All right, so yeah, let me see your pictures. I'm going to see. All right, so here's a thought exercise. Okay, so you only get one answer per person. Okay, and it gets harder. We're playing the game, right? We're playing a game. Okay, here's how the game works. I have 2 devices that are in the same room, and I want to connect them together, okay? Without, I'm sorry, that should have said without. Okay, I don't want to tie the grounds together. All right, it gets easy. The first couple are kind of easy. And the last few are hard. So if you want to, so unmute yourself and give me a way to connect 2 devices in the same room.
Differential voltage.
No. I mean, how does a differential volt and okay, so it's got to work with 4,000 volts between the 2. Differential voltage doesn't work. It'll explode if nope. Good try.
You can't take like the difference between 2 lines.
But you have to generate a common ground. Voltage is only, even a differential voltage. I don't want any current flowing from one to the other. I don't want current coming out of this knob, out of this power supply into that ground. So I will charge you to think about it for a while and to figure out if it would work, right? If you did a differential drive voltage through into an instrumentation amp, okay, there's an implied ground connection, whether you wanted it or not. This will only work if they're in the same ground. Okay, so I'm gonna quit this. Get rid of it. I'll let you think about it. You can let some other people answer, and let you think about it again.
Is it,
Cable
do we
shield.
have to use wire? Can we not use wire? Like,
Okay,
Bluetooth or something.
you want to use wire? You can use wire. I got 2 devices in the same room. Okay.
Cable shielding.
How do you shield the cable? Yeah, the grounds are connected. Okay,
Isn't that what you want?
no. Okay. If you shield the cable, you still, in order to get bits from one box to the other, the shield and the cable don't help nothing. Okay.
I think a lot of people may be confused about what you're asking.
Okay, so let's do the elephant in the room. What have we spent 99% of the time in this class doing?
Wireless communication.
Wireless. There you go. Okay, so whoever said it gets yeah, wireless.
What do I get? 300?
You get points. Yeah, that's the easy one, right? Wireless, RF, right? Electromagnetic field in the RF plane sending EM across the field, and now the grounds are not tied together. Okay, and
Fiber
data can flow.
optic. Fiber
Which one?
optic.
Yeah,
Fiber optic.
light, fiber optic. There you go. See, now we're on that. So basically, you have a light emitting diode here through a cable. and then you have a light sensitive transistor over there, and you know, you can send bits, fast, reliable, whatever. Good. It's getting harder.
Sound.
Sound, sure could, sure.
So are you talking about like bridging the air gap, I guess? Is that what we're talking
Well,
about?
no, some of them are going to have wires in it. You don't have any wired ones yet, and you will. Yeah, you can send sound. An interesting one that's sort of in this thing is, well, I don't know. I'll get no. It's sound works. Sort of sound encoding. Yeah. So we did that. I did that for the robot. Was one of the, remember the robot with the round thing with the, I put microphone on one and a speaker on the other, and one would dance and play a sound and the other one would synchronize to it. Because I would frequency shift key the sound, the audio sounds, and the other could pick up what sound it is with a Fourier transform or whatever, and then send commands across in the frequency domain. Sure. Yeah, sounds good. So if you answered one, don't answer another one. Let some other people answer. Want a hint? Okay, you don't want a hint. You want to think about it. There's one that works underwater, and it works inside the body.
Ultrasound?
Ultrasound, okay, fine. Ultrasound I'll let you have ultrasound. It's not quite the same as sound. That's ultrasound.
Wait a minute. It's pressure waves.
Yeah, it's sort of
Lasers.
pretty much the same thing, but it's because I'm going to give you one that's very similar to one of these other ones, by the way.
Maybe infrared, but
Infrared,
is kind of like,
sure. That's like your remote control, right? IR. It's actually very similar to this, except there's no cable. An IR LED to a light sensitive transistor, right? Your remote control.
Lasers,
Which one? Okay,
lasers.
okay, lasers. Sure. I'm not sure. How do you? What's on the laser comes?
You just
Laser.
beam a laser to a receptor and then you pulse it.
Sure. Laser, good. I'll take that. I take that. Okay, so, I need this spot in my thing. Yeah, let me show you the way that we if you put two embedded devices inside a human body, okay, and you inject a current. This is an electrode, and that's an electrode, and you basically drive current. This is the circuit. Okay, I put the circuits here. These are two platinum or gold connectors. That's the circuit. This is the body. Okay, and you inject current into the body. You can, and that's kind of what Keyshawn was saying. And you have a second circuit somewhere else in the body. You can pick up those waveforms. So if you modulate this guy here, for instance, is modulated at 30 kilohertz. A typical remote control is a 30 kilohertz modulated waveform. You can do the same thing here. And actually send bits from one object. But in all fairness, the grounds are implied, and so it will create a common ground here. This circuit does this. So in all fairness, these grounds are they're not wired together, but they're implied together. Let me just do another one. Got any more for me? All right.
You have an accelerometer on one device and the other device buzzes.
Okay.
And the
Now
accelerometer picks up the vibration of the other device.
ooh, yeah, I like it. I like it. Sort of vibrations. So you sort of stamp your feet on the floor, right? So you have a plunger, and yeah, sure. Yeah. So you bang. Yeah, you bang on something solid, the floor or whatever, and you pick it up and accelerate. That's nice. I hadn't done that one. Okay, you guys aren't old. You guys are about 20 milliamp current loop is the, if you, this is a wired connection, okay? The grounds are not tied together, but what I'm going to do is send 20 milliamps of current through here, and now the device over here can either optically connect, okay? It can either be optically or connection. So it takes two wires to send information, but neither is ground. The
That's
one we're going to do, anybody want to do one?
By the way,
What?
that's still around, by the way.
I know, but it is one of the things that happened, one of the first serial protocols that came out in the 60s or whatever, when people hooked computers up together.
So can you explain why differential doesn't fit under this?
Well,
I'm a little,
it's just see, the point is, okay, so, okay, yeah, I can. Okay. Okay, so you've got a differential driver here, right? So this is, say, plus 2 volts, minus 2 volts relative to this ground. Are you with me? Okay, that's a differential driver.
yeah.
Okay, so you got a plus 4, you got a plus 4 volt differential output. Okay, and
Measured
you're
against the 2 wires, yeah.
with 2 wires.
Yeah.
Okay, this guy has got a power to it, 3.3 volts, and a ground. Let me just draw a different ground. Okay, and this is an actual chip. All right, you with me? This is an actual chip. Right, this is and so what is the rules of a rail to, what is the, if you call this V1 and that V2 relative to this ground, what's the rule, right? V1 has to be less than the, this is ground B and voltage B. But this is voltage A and ground A. So in order for this constraint on this instrumentation amp or op amp or whatever you want to call it, in order for that to be true, the ground in A has to be essentially equal to the ground in B. And obviously you can't have minus 2 volts here. Can I make this minus 3.3 volts? Whatever. Let's make this 1 and make this 1 and 2, and so we have a differential plus 1. I can't get minus 2 out of an op amp with driven 3 volts and ground. Okay. These two grounds. The way here's something we do with the medical. This is one of the medical safety constraints for this problem. And as I said before, does this work with 4,000 volts between the two? If I take a 4,000 volt power supply and I connect the two grounds 4,000 volts apart, will it still work? And I would contend with everything we've done thus far, other than my body translator, the ultrasound, the wireless, the fiber optic cable, the current loop. Again, the current loop works because there's an optical link here. Now the LED is in the receiver and not in the transmitter, but it still will work. This device here will withstand a 4,000 volt gap. And so that's what I mean by connect devices without the common ground. All right, I got one more, because, I mean, just to remind you here. I got one more just to remind you. Do you see a ground in here? No, you don't. There's no ground here. And it sounds like what Keyshawn said at first is it's differential, but it's differential with a transformer couple. Okay. So if I energize this, if I energize these coils, the mutual inductance. Now, again, you can build these. Now, I don't necessarily think of an Ethernet device can withstand 4,000 volts, but they do not require the grounds tied together. And there's some really cool, yeah, let's show it to you. There's some really cool ways in which these grounds are connected. And this green thing is the voltage isolator on the device. So to essentially create a differential voltage on transmit plus and minus, okay, such that the digital signals here on these two pins are inducted, mutually inducted over to a differential voltage over there, such that the grounds in this system don't need to be connected to a ground in the other side, the other mirror image of this on the other side. And it uses mutual inductance because that allows you to send signals through a transformer that don't require the grounds tied together. All right. Every time I look at one of these, okay, every time I look at one of these things, I see a little bit different protocol. Okay. So this is the Ethernet frame. You can see it has both the source and destination address, the length, and a frame check code. I got one more thing I think I have to do. Yeah, this is another fun exercise. You probably know what a MAC address is, right? So what's a MAC address?
It's the media access control address, and it's usually the specific device address of your.
Yeah, every device in the world, okay, every device in the world has a MAC address. Now, when you buy it from a company, right, and you don't erase the flash, or if you read the flash before you erase it, these Wi-Fi devices, things that get on the internet protocol, either an Ethernet device or a Wi-Fi device, if it gets on the internet, okay, it has to have a MAC address, okay? Now, scoundrels will go spoof those things, but real people buy them, okay? Accept and close, okay. All right, so if you were just a regular guy and wanted to buy some, let's look at the cheap ones first, okay? So, it's just sort of like, what do you do? What do you do when you're sad, right? You get onto Amazon and you buy stuff, right? That's what makes you happy. And so what do you do if you don't want stuff? You can buy MAC addresses. Okay, so the small block MAC address is basically one, there's 48-bit thing, well, or a 64-bit thing. But anyway, you get for the small price of, for the small price of $800, and then you probably an extra 200 and renewal fees and whatever. For a small amount of money, you can get assigned to you. So if you got a 48-bit MAC address and you've got a 36-bit fixed number, that gives you 12 bits or 4,096 different MAC addresses that are now yours. Okay. Well, if 4,096 is not enough, okay, then you can go to the big one. The big one here. Okay, where'd it go? Where'd it go? Where'd it go? Where'd it go? The large block, okay? A large block of MAC addresses. Now, obviously, you're buying them from somebody. A large block basically gives you what's called a organizationally unique identifier. And that's the first half, the first 24 bits of the MAC address identifies your company, organizationally unique identifier. And then you get the other 24 bits, which means now you have 2 to the 24th or 16 million different MAC addresses for your pleasure. And but that only costs you $3,000, okay, plus $200 plus a renewal fee and all the other stuff, because you know how it is. So yeah, here's the warning when you buy IP whatever IP ready devices, they from a reputable place, it comes with a MAC address in it. And so one of the good ways to use it is to read what it is first, because if you brick the device and have to re-flash it, you could potentially lose your MAC address. Okay, so that was my advice to okay, so all right, so this is the demo I'm going to do. I got to go in and get it, and basically it's a web server, and there's a second document in the folder. There's a second document in the folder that's a doc file, which is essentially the same stuff we just did, but with the words from the book. And in particular, this is actually the same information we just did. But when it gets down to the demo, okay, it basically describes the way in which I built the demo, together with the code and crap. I was going to demo this thing next time. But all right, I'm out of slides. Any questions? I'm done. Sorry. There's a lot left in chapter whatever chapter number chapter 6. Yeah, we're going to do the Wi-Fi. I'm going to do the demo. I'm going to do the Wi-Fi. 802.11. We've got some low pan. We got a low pan lab in the works. We'll talk about it. Yeah. Questions? All right, I'm going to, okay, stop recording. Stop recording.